In Chapter 33, we're going to continue to study induced effects. So induced current, induced voltage, time rate of change of flux, Lenz's law, that all still stays in play. What we are doing now, however, is going to be to introduce new parameters, these L and M parameters, which I'll get to in a second, that is going to give us a new mathematical structure to use to make the same types of calculations that we've been making with inductance, but it simplifies the mathematics and the calculations. And we will see how that works out. For right now, I would like you to absolutely make sure you get this bit over here down into your notes, because the logic structure we are going to use and the equations we're going to generate, we've seen before. With capacitance, we saw that the charge on the capacitor was directly proportional to the voltage across the capacitor plates. So we double the charge, we double the voltage. That allowed us to introduce the proportionality constant C. Well, we're going to do the same thing now with flux, so we're going to see in our next lesson, so I'm jumping to the punchline here a little bit, that the magnetic flux through a coil will be directly proportional to the current running through the coil. And hopefully that makes sense based on what we know about current generating magnetic fields. The B field in a solenoid. A solenoid is just many coils. So the flux, magnetic flux through the coil will be directly proportional to the current, and we're going to introduce the proportionality constant, which we call L, for that coil itself. Therefore, that's a self-inductance. The mutual inductance will be a situation like we have up here, where we have two coils, and they will mutually affect each other, but we'll get to that later in this chapter. So just like the capacitance was a strength parameter for a capacitor, in other words, the capacitance told us how much charge per volt there was for that device. So the larger the capacitance, the more charge per volt. Self-inductance is going to tell us the same thing. It's a strength parameter. The self-inductance L is going to tell us how much flux per amp there is through a coil or for a solenoid, and we're going to begin to refer to solenoids now as inductors. So a solenoid is going to be our prototype of an inductor. So this is the game we're playing. This is the mathematical structure that we're going to establish. And I wanted to get that down up front for you so you kind of have that to work off of as we begin our explanations in this chapter. Now, what I have down here, I realize your page is blank and there's a lot written. So let's take this one step at a time. The first thing I would like you to do is just focus, just write in the blue current I sub B that begins to appear right at time t equals 0 when the switch is closed. We go from no current I sub B to now having current I sub B. And when the current, B for battery, from the battery begins to flow, we will get B field generated in the area that coil or loop makes. So the area generated by the circuit itself is going to be seeing a time rate of change of flux. And just to remind you of the Biot-Savart law and IDL cross R hat, your cross product, let's quickly get in a little IDL here. Let's put in an R hat here, and let's practice our right-hand rule because that's so important for magnetism. So you're going to do IDL, you're going to curl, so your hand's in an awkward position here, but right hand, IDL cross R hat, thumb out of the paper, so we get B field out of the paper beginning to make flux through the circuit itself when the current begins to flow. Well, that time rate of change of flux, now we can begin to get in the notations over here. That time rate of change of flux from the blue is going to introduce an induced EMF, an induced current, clockwise to generate a B field into the paper to try and keep the status quo. The status quo was no B field at all. And now the battery current is making B field out of the paper, and nature is going to apply Lenz's law and make B field into the paper to try and keep that status quo by going clockwise. So please get all of this into your notes because we will be using this in the coming lessons in this chapter. And also please get into your notes this bit over here, this exploded comment, because right at time t equals 0, you have an enormous change in the flux. You go from no flux to some flux, nothingness to somethingness. That's huge. That's an enormous change. And the induced EMF right at time t equals 0 for that one instant only will match the current trying to flow. And sometimes solenoids, which we're now going to interchangeably call inductors, these solenoids inductors will choke off that current to stop the flow, and actually inductors can be used as kind of a surge device for these spikes in changing current, especially for high frequency ones, as we'll see. And this is going to give us our structure, our basic understanding to develop our new structure with the L parameter that we're going to introduce in our next lesson. We can also see, just as kind of a little bit of a side note here, that electrical engineers, when they design circuits, now you will understand why they have to keep these areas small, right? They don't want a big circuit unless you're going to deal with the induced effects from having a large flux. So one of the kind of adages in electrical engineering is keep the leads short, keep your wires short. You want your circuits to be small so you do not generate a large flux area, which will generate the induced EMF, because that makes for noisy circuits. Maybe this current isn't coming from a battery, it's coming from a signal or a source where we want to preserve the signal. We don't want it corrupted by the induced effects. So I realize there was a lot going on here, and of course, if it's highlighted and starred, that's always important to get into your notes, because once the battery voltage, in our example up here, has reached a steady state value and there's no changing flux, well then of course there is no induced effects. So I'm going to zoom back out here for a moment. It's our introductory page to chapter 33. Please copy this down in detail so you have it as I'll reference it through the rest of this chapter, some of these concepts. And it gives us a good starting point to understand these new L and M parameters.